Good afternoon and welcome to CIM webinar, Making Tailings Coarse Again, Mining Technologies that Coarsen the Size and Reduce the Quantity of Tailings. Our panelist presenting today is Brent Hilscher, Vice President at ABH Engineering. My name is Guylaine Richard, Professional Development Officer at CIM, and my co-organizer is Michelle Beacom, Managing Editor of CIM Magazine. On behalf of all of our colleagues, we thank you for joining us. Some housekeeping before we get started. If you joined with your computer audio, make sure you selected the computer audio button on your control panel. And if you dialed in with a traditional phone, ensure the phone button is selected. If you have any questions during the presentation, please type them into the question box in the control panel. The questions will be held until the end for the Q&A period. And now, without further ado, we'll turn the webinar over to Brent to kick off the presentation. Thank you for joining us, Brent.
Thank you for having me. Can everyone see me okay?
Yes.
Awesome. So let's see here. Today we're talking about making tailings coarse again. And it's kind of a cute title, but it has real world consequences. So we'll start with who am I, who is ABH? So I'm a mineral processing engineer. ABH is a small engineering company focused on mineral processing and on improving mine economics through new technologies. And making tailings coarse again. So in the beginning, only the coarsest of the highest grade rocks were processed. They were picked by hand, they were mined by pickaxe, and then technology advanced year after year, and we were able to grind the material, grind finer and finer. And as that material could be ground finer, the cutoff grade decreased, and we were able to access lower grade deposits. But this led to some consequences. And those consequences were not all good. Some were good, lower metal prices, but some weren't great, more tailings. So we'll start talking about why this matters. We'll look at some videos because everyone likes to see videos of how these things work. Some of the concepts are a little abstract until you can watch them happening. We'll look at some of the new coarse technologies that are out there. We'll look at some of the benefits. We'll look at some of the ways that we can measure this. And then we'll throw in some kitten pictures because some of this can be pretty dark and depressing. So it's good to lighten things up a bit. So why do fine tailings matter so much? The more fine tailings you have, the more dams you're going to have. The higher the volume, the higher those dams are going to have to be. And that leads to a lot of risk in terms of failure, especially when you start with a dam that's this high and then you add a little more and a little more. And now the founding designers are looking at something that's not quite like they designed. So if you can dispose of more of your mined material in a coarse pile, you're going to have it be mechanically safer. It's going to be more economical because piles are easier to reclaim. You'll have fewer dams, you'll have less power, less CO2, less water, all those good things. And yeah, reclamation will be a lot simpler. So as metal prices increased a little while back, a lot of the all kinds of mines, but this graph just shows copper mines, have been increasing. So there's more mines than ever before. So this is, here, I'll take my coat off here. This is an interesting graph though. This shows serious failures and it's been increasing. This is since the 1960s. So severity and frequency of failures. This isn't getting better. We've got another graph showing something similar. This is the 100 years of failure. This is how we're failing in two different ways. The amount of volume that's been released from tailings dams due to catastrophic failure, but also the loss in human life from those tailings dams. Technology's been getting better. Our ability to build dams is getting better, but these numbers aren't. So there's a serious problem that we need to look at here. Oh, and we've got more unfortunate data. So, well, I mean, some of this is good. We've seen a 87% decrease in cost of mining, which is great. And that's led to lower cutoff grades. That's led to everyone in the world being able to basically afford mined materials. But it's also led to a very large increase in tailings. And just even recently, 2005 to 13, we saw the minimum gold grade or the average gold grade drop. So that means for the same bar of gold, you need to process an extra 30% of material, which means an extra 30% of tailings. So some stuff to think about here. It's not getting better, seems to be getting worse, but we do have some technologies out there that can deal with this. If you can't eliminate the ponds, at least you can make your pond smaller. A smaller pond is definitely a safer pond. And so we're going to look at a few things here. We're going to look at ore sorting, which is one of the newer ones that everyone's very excited about. We're going to look at coarse particle flotation, and then some dense media separations. Then there's some other technologies that aren't exactly processing. You've got co-disposal, where you take your now larger rock pile and you pour in fines into it, or you co-dispose. So you put the fines and the coarse into a pile at the same time. Paste fill, dry stack tailings, centrifuge paste, all of these things can help. All right, so some multimedia, because it's always nice to see some pictures. This is, of course, the original ore sorting, optical. People would see a high-grade rock and pick it out, and that's what would get processed. It was an easy way of saving power, very practical if you had cheap labor. We've come a long way. Here's the new XRT machines. I'll turn up the volume so people can hear it. So what this does is it takes rocks from the conveyor, spreads them out through the feeder on an extra wide conveyor belt. These things can be 2 meters wide. By the way, not my technology. I just help people figure out if this is a good one for them. So here we've got X-rays scanning each particle as it flies past. These are going a couple meters per second. The computer makes a decision on each particle, whether it's worth keeping or throwing away. If it's worth keeping, it tracks it, and as it falls off the edge, it's put into the keep bin. Otherwise, it continues on its existing trajectory. And the accepts and rejects, it's determined by mass pull. So if you want to reject whatever's less than 50%, maybe save on error costs. And I have seen an operation where 15%, 10 to 15%, actually a few operations, 10 to 15% of the ore was worth keeping and everything else we threw away, just because it was below cutoff grade and they were losing money on it. Oh, here's my first silver operation. I like this one. It's on an old iPhone 5. So I think here we were looking at about 20% of the ore was worth keeping, everything else we threw away. This is a neat one because it's mechanical diversion. This is a Rados machine, so as the rocks fall, again, they're tracked, and mechanical clippers divert it. Okay, this one is a bulk conveyor diversion system. There's a few different technologies that do this. This one is called prompt neutron gamma activation, where neutrons impact the elements in the conveyor, on the conveyor. Those elements re-emit a gamma ray specific to the atom that you were emitted from, and then you just detect those gamma rays, sort of like an AA machine. Very accurate, but you're diverting all the material one way or the other. So it's not quite as selective as particle sorting, but it is insanely cheap. So if you wanted to do this on, Escondida, no problem. It can handle the tonnage because it just, whatever's on the belt gets sorted. This is a typical configuration of a particle sorting system. You've got your gyratory or your jaw. The material is usually 1/2 inch to 3 inch, although the manufacturers are always pushing the boundary. So I'm hoping that we'll see 5 or 6 inch sorting soon. The liberation due to size, usually not the same sort of problem that you would think it would be, because we're sorting by rocks, not by mineral grains. Oh, this is hydrofloat. This is a neat one here. It's another video.
Instead of an agitated slurry, it uses a aerated fluidized bed. The air and water are injected into the fluidized bed. As the air rises up through the bed, it collects the coarse, valuable particles. And once the bubble particle agglomerate gets light enough, it's then transported with the water up to the top of the cell and gently overflows into the concentrate. So essentially, the hydrofloat project allows us to recover copper and gold that we couldn't with the previous technology.
So again, this is a technology where instead of producing very fine sand, maybe you can create fine gravel. Gravel, very useful for roadbed materials, and you could even do a bit of co-disposal with it. So it's much less impact on your tailings pond.
Instead of an agitated.
There we go. We don't have any videos for gravity separation. We cut them for time because everyone knows how jigs and Nelsons and those sorts of things work. But again, these are also technologies that can help you dispose of your waste while it's still coarse. So here we've got an example. This is oversimplified, but that's okay. Usually we'll start with 1 ton of ore, we'll turn it into a ton of fine tailings and put that in the pond. Now, if we put an ore sorter here, we divert half of it in this case. It's an aggressive sort, so this might be an underground gold operation or something like that. Now your pond is half the size. That's fantastic. Now, what if we did co-disposal? Well, now some of those fines can be disposed with some of that coarse rock. Congratulations, you're getting close to eliminating your pond. Now, we take some of our regular waste rock, which most mines will have some of. You mix that in with your rejects from your ore sorting system, and hey, congratulations, you've eliminated your tailings pond, you win. Now, you might not have any spare waste rock. Which is this one? All right. So some of the other benefits, obviously eliminating the tailings pond is great. What else can you do with pre-concentration? What other benefits are there? So yes, you can save OPEX, CAPEX, use some new technologies for tailings, that's great. You can increase your mill feed rate. That's always a big driver for these technologies. Your OPEX per unit of whatever you're producing will decrease, your metal production will increase, and of course that just has a huge impact on profit because your production is increasing while most of your costs are staying pretty much the same. Less selective mining is always a nice one. This is basically lowering your cutoff grade and changing your mining method to something a little cheaper. Lower OPEX, lower CAPEX, and a lot more tons being provided to the ore sorter to help the ore sorter increase that metal production. This is the lower cutoff grade. Here we really look at the reserves going up, which is a big deal for most operations, unless you already have 20, 30 years mine life. So there's a lot of other benefits that we don't always focus on. The footprint of the plant is a nice one. If you can do ore sorting, your processing plant, especially if you're greenfield, is going to be smaller. You're going to use less water. You're going to use less power. You're going to emit less CO2. Then there's going to be an impact on your social license. So if you can go to the local communities and say, you know, the previous design had a tailings pond and this large mill. This new design, no tailings pond or a much smaller tailings pond, much smaller mill, same production, same jobs. That's going to be a popular thing. So this section's a neat one. This is something we did to help us measure success in ore sorting. There weren't a lot of easy to understand, easy to calculate metrics. So this is profit recovery. This looks at your metal recovery graph and says, what if we included tailings costs and milling costs in this? And this is what we get. So this is one of the Barrick mines that I did. This is their standard grade recovery curve. And this is something that I output from the ore sorting projects I do. I've done like 50 of these. So as you move from the right to the left, the computer tries to put all the low grade rocks on the right, all the high grade on the left. Here you can see it does a pretty good job until around 50%, where it starts making some mistakes. But generally, this is a lot better than our block model was. And this is looking for gold through associated elements using XRF. Now, if we incorporate operating costs into this, we can see we start around 50%, and then we go up and up and up and up, because as you reject these rocks you're losing money on, you're losing traces of gold, but you're saving a fortune on processing. There's some little dips in the middle there as we lose a good rock, but then we throw enough waste away, it makes up for that. This is El Gallo. This was a McEwen mining project, and again, you see very nice sort. The computer does a spectacular job putting all the high grade on the left, but the operating costs are a little lower. So the increase in profit recovery is a little more gradual. And keep in mind, this ignores a lot of the other benefits that could be had here. It ignores the increase in production. It ignores changes in resource and mining method. This is just the very simplified minimum benefit. This is a new gold deposit that we did. Here we almost hit 100% profit recovery, which is lovely. Again, a very nice clean sort. This one, Operation A. So I was allowed to show you the data, but I wasn't allowed to tell you whose it was. And we're almost done here. This is a 32 pack, which does 6,000 tons per hour of particle sorting, just to show anything is possible here. Usually if you're doing 6,000 tons per hour, though, the first thing we'll look at will be a bulk sorting method. But it's important to build economic models and then let those economic models tell you what makes sense. A lot of times, common sense and gut intuition will lead you astray. So we always build a model to give us clarity on what is really the most economic thing to be doing here. And that's it. Oh, and I promised some kittens. So puppies, minor. Oh, there we go, kitten picture. Thank you for making it through the presentation.
Thank you, Brent. Very interesting presentation.
Thank you.
So we will now start the question period. And just as a reminder, please type your questions into the question box in your control panel. So we'll go with the first question here, Brent. What percentage of new mine designs could eliminate their tailings pond fine?
I find probably 50%-ish. It's the question is really how many could eliminate their tailings pond while still making their project more economic. 100% of deposits could be without a tailings pond, but a lot of them, it's unrealistic to expect that from that particular deposit. So I'd say at least half, it really makes sense, even if you ignored the social license, just from an economic standpoint. You want to get rid of that pond. It's expensive, it's a liability. You got to give the government bonds for future reclamation. There's a lot of costs associated with those things. And if you can eliminate that, that'd be fantastic.
Okay. How the detected gangue rocks are separated in the sorting machine?
It'll depend on your deposit. There are, at least a dozen technologies out there. There's XRT, X-ray transmission, which will look at density. So that's great if you have sulfide minerals or sulfide associated gold, silver. There's laser, fantastic if you have a quartz deposit, quartz associated gold. There's infrared, ultraviolet. I use those with diamonds. There's PG&AA and XRF on conveyors, which are great for diverting open pit ores. There's XRF particle sorting, which looks at the elements, and some of the more selective machines can do down to detection limits where you can detect silver in a silver mine and do a silver-based sort. So it depends on your deposit.
Okay. There is still an issue with ore sorters, low throughput, many machines for high throughputs. So what do you think about the bulk ore sorters applicability in the near future?
Oh, they're fantastic. I'm trying to do a big push on bulk ore sorting in North America and South America right now, where we'll look at the mine in a holistic sense and say, look, if we can boost the mill feed grade by even 15–20% using a bulk sorting system, what does that do to the economics? Particle sorting, you're still limited to 200 tons per hour per machine, but I don't know if you can still see my slides. That last slide, the 32 pack, 6,000 tons per hour, is plenty big for most operations.
And how have you stored the processing water?
Oh, so this is where you eliminate your tailings pond. So yeah, you're definitely still going to have a pond. A lot of operations have tried eliminating ponds, and you get into a situation where you have salt buildup much faster than expected, and that interferes with your extraction technologies. So you'll still want a sizable pond, but you want it to be a water pond, or perhaps a polishing pond where you recover some clays, something like that. It'll still need to be pretty big though.
How much is the cutoff size of coarse and fine for the ore sorter?
So it's not so much a technical cutoff as an economic cutoff. So the better the business case for particle ore sorting, the finer we push that cutoff. So usually it's ½ an inch, but if this sorter is making a ton of money for the mine, we could push that finer. And for for bulk sorting, of course, there is no cutoff. Everything gets sorted with a bulk sorter, which is one of its advantages.
How do staffing levels remain constant with a reduced TSF size volume and mill size?
Ah, that's a good one. So in your mill, there's a temptation to think that if we build a mill half the size, we'll only need half the people to staff it, but that's never the case. It's almost always just about the same number of people to staff it. If you have a ball mill that's twice the size, it doesn't require twice the labor to maintain or to operate. So you'll have your grinding operator, your extraction operator. So the staffing won't really change, but the profits will. If you can produce double the metal out of the same mill, you'll make a lot more money.
How many operations are now using large tonnage coarse separation?
Trying to figure out, does this mean bulk sorting or particle? But I'm not sure. I'd have to get back. It's many. But it's been a while since I put together the grand list of all the world operations. 5 years ago, I think it was between 50 and 100. Now it's much more.
And can you say more about the specific methods that the studies shown in the data sets used to pre-concentrate and reduce or eliminate the TSF?
So I'm not sure what they're asking here. Each one uses a different ore sorting method, XRF, XRT, infrared, EM. And then by rejecting coarse material, and this is often size classified coarse material. So if everything's put in a pile between 1 inch and 3 inch, there's a lot of space in between those particles, which means the material you are processing through your mill, because you always have to grind up some of it for flotation or leaching. So that material can then typically fit in those spaces, especially if you've got a very large amount of coarse material and a rather small amount of fine material. Hopefully that answers the question. If not, give me a call and we can chat later.
Does the recovery drop as the ore sorter is added to the flow sheet?
Depends how you measure recovery. So it gets very complicated. Your profit recovery goes up. Your metal recovery goes down one way you measure it, but it goes up another way you measure it. So if you say, okay, we're going to put in the ore sorter, it rejects half of the mined material, but you lose, say, 5% of your copper. Well, that's not a bad deal. Your material being rejected is 1/10 of the average grade. That's definitely waste. So it's good to be throwing that away. But you still have lost 5% of what would have been milled. Was it waste? Yes. So if you throw away waste and it has copper in it, should that hurt your copper recovery? It's a neat question to be asking. And then if that lets you lower your cutoff grade and perhaps your resource doubles, now you have twice as much copper, but you're throwing away 5% of it. What's your recovery now? So there's a lot of ways we can go about calculating things.
And what metals have you worked with using these technologies?
I may have lost count. We've got copper, lead, zinc, silver, gold, more gold, platinum, tungsten, cobalt, and diamonds, of course. And there might be some that I've missed. I've done 50 projects and they're all starting to blur together.
What is an order of magnitude or ballpark cost for an XRT for a 10,000 tons per day mine?
5 million.
How can you have coarse particles if you need to grind more the deposit to achieve the liberation degree?
That's a good one. So there's two levels of liberation here. There's liberating valuable rocks from waste rocks at, say, the 3-inch level. So that's your first step, and that's where the ore sorters or the a lot of the other technologies will come in, is saying, okay, this rock contains no valuable minerals, let's throw that away. And then you've got your liberation as we normally think about it in flotation or leaching, which is we want to expose a certain percentage of the mineral so that the extraction can take care of it. Does that answer the question?
Let's hope so. And do you still need to remove water before to mix the coarses with the fines?
There is a target density for co-disposal. So you have to manage that. And then when you place the pile, there's some runoff as it settles.
Do you have examples of ore sorting projects that started with tests or only drill core? Do these amenability tests scale up well?
So usually we'll start with the drill core, and there's several stages of testing. So we'll start with, say, 200 pieces of broken drill core. We'll scan them and we'll assay them individually. That lets us get a very, very good grade recovery curve and a very, very good algorithm. So it's not a representative sample by any means, but it does give you a very good algorithm, because if you lose a particle that has, say, gold in it, you can look at that particle, say, what in that scan should have tipped us off that this was a valuable rock? And you can tune your algorithms in that way. And then in phase 2, now you get tons of material. And the largest I've done was, I think it was 2 20-ton samples. But usually 1 or 2 tons of material is fine. And that can be broken drill core, it can be grabbed off of conveyors over a number of days. But that's where you start getting into creating something representative, and that's what you need for a feasibility study. Whereas particles, 200 rocks, scoping study level is fine, but once you get into feasibilities, now you need something more representative.
And would a sorting system combined with a dry stacking method be a potential hybrid approach?
I think so, yeah.
Are mass pull and recovery factors typically changed by software adjustments or by equipment modifications?
It's all in software. And you can even tie it into the metal price. So as say if you've got a zinc deposit, as zinc price changes, the ore sorter is measuring, and that cutoff is always has at its root a $1 per ton target. So as the metal price changes, if the price drops, you can lower that cutoff, requiring the ore sorter to only take the most valuable material, because economics have changed. So that's a good question.
Where's the 32-pack sorter installed?
Oh, that's just on paper. That hasn't been installed yet. But we could. Happy to.
What's the water quality in the remaining water pond?
That depends on your operation.
What is a typical error percentage for an ore sorter to falsely discard a value particle in a single pass? Can additional recovery be achieved by recycle streams and or additional sorters in series or parallel?
So depends on the vendor in a big way. So I've grossly oversimplified the role of ore sorting to fit it into a short presentation. 2 to 6% error seems reasonable, but each vendor will have a different error. What was the rest of the question?
Can additional recovery be achieved by
Yes.
recycling streams?
So the answer is yes, but when you run the economics, it's rarely worthwhile, because a lot of the mistakes being made are with the marginal grade material. So something was close to the cutoff grade, above cutoff, but not that far above. So it accidentally got rejected, but really you didn't lose a lot of opportunity. You didn't lose much profit on that rock. But yes, in some situations you will put in a second ore sorter, and a lot of cases you'll use a different sensor. So the initial ore sorter might use XRT, scavenger might be XRF. It is a possibility. We can also put these underground.
Which kind of deposit you consider the best scenario for better performance of ore sorters, and which deposit could be considered a challenge?
Let's see. I love the sulfides. Those are always very easy. Anything underground has always turned out to be sortable. Open pits and porphyry do very well with bulk sorting technologies. Probably the toughest type of ore I've seen would be the oxide heap leach for gold, where you might have really good variability in grades, but there might not be anything that the sensor can see to predict where the grade is going to be in that rock, because all of the indicators have been leached away, oxidized.
By going coarser, there are also some geotechnical ramifications when it comes to tailings dams construction. Can you please comment on the pros and cons for TSF construction, please?
Well, I'm not a TSF engineer, but generally coarser has always, as far as I've been told, been a big benefit. The material going to the tailings pond itself is still going to be the same size distribution. So your milling process will still have the same target grind size, might be a little bit finer if anything, because it's a more valuable feed. So you're still going to have those fines if you have a tailings pond, but you'll have more coarse material besides that. And that material you can use for road construction, for dam construction if you need more coarse material for the dam. But it is something that the engineers will have to look at.
What is the minimum mass rejection for a feasible pre-concentration?
Depends on your economics. That's why we always do the economics. Ties in closely to recovery. So recovery, I tend to think, is more important than the absolute mass pull. But anything over, 20% upgrade is usually a clear win. With bulk sorting, it's a much lower bar because bulk sorting costs 5 cents a ton or less. So any improvement, any measurable improvement by bulk sorting is going to be economic.
What about recovering 2 or more products?
Yes, we do that quite a bit. So you might have a deposit that has a sulfide zone and an oxide zone. You want to take the high-grade sulfides and send those to the mill. But then there's some high-grade oxide. You don't want to send it to the mill right now, but you do want to put it in a pile to deal with later because there's value there. So what we'll do is we'll either put in a sorting system that has a 2-step built into one unit, which is fairly uncommon, or we will put 2 in a row, one to remove the sulfides and one to remove high-grade oxides.
And one last question. What are the variables that are considered in the calculation of the profit recovery index?
So it's definitely oversimplified. It looks at your grade. The grade is turned into value per ton of that rock. And then the cost per ton of mineral processing and tailings is subtracted from that. Mining costs are already sunk, so those are ignored. So that it's just a nice way of saying, oh, this rock can go negative. So even though there's metal value in that rock, there is a negative economic value in that rock. So we should throw that rock away. Even if it costs us a little bit on metal recovery, we are wasting money. And we could replace that rock with something that if not valuable, is at least less detrimental to us, if nothing else. But yeah, ideally you replace those rocks you're losing money on with rocks you would make money on.
Well, thank you very much. Looks like we've almost run out of time. If your questions was not answered, or if you have any further questions, please forward them to Brent, whose contact information is on the screen. Brent, again, thank you for being with us today. I'm sure you'll receive many follow-up questions.
Hope so.
I'd also like to thank all of our attendees. Please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording will be emailed to you tomorrow. And the video will also be available on the CIM website. So again, Brent, thank you, and to all, see you soon.